To the Unit 1 guided practice for remediation. This is designed to help you develop the tools necessary to be successful on Unit 1 material, especially since we will return to it throughout the course of the year. The first thing that you need to be able to do is you need to be able to convert numbers into standard notation. So standard notation is something like a number like 125. That's what we call standard notation because there are no times 10 to the something. So whenever you put a number in standard notation, what you do is you look at the exponent. Okay, when you look at the exponent, that tells you the number of places that you are going to move the decimal place. Now, if it's a positive number, so if it's a positive, like we have here, a positive plus 4, what that means is the number is going to be very, very, very large. In order to make the number large, I have to move the decimal to the right. So what I do is I say 5.0, and then I move the decimal 1, 2, 3, 4. And I put my decimal in that fourth one. Now in between these little dips right here, you have to put a 0 in each one. So I have 0, 0, 0. Or if I were to write the number out, I would write 5, 1, 2, 3, 4 zeros, and then I would put my comma in there and I would say 50,000. Now it's really important that I put the unit there as well, so I'm going to say 50,000 meters, and that is my final answer. Okay, in the second one, notice that it's a minus 3 times 10 to the minus 3. Whenever you have a negative exponent, that means it's going to be a very, very small number, and so the exponent's going to move to the left. Whenever you do this correctly, you should end up with something like 0.0075 grams. And the final one, if you can do correctly, is 8600 000 000. Now when you're doing these, please make sure that you don't just copy the answers down. Make sure you understand how you get from this to this. And if you still don't after watching this video, make sure that you seek help from your teacher. Okay, next it says convert the following into scientific notation. So we're going to do the exact opposite. We have the numbers that are written in standard notation right here, and what we want to do is we want to put them in scientific notation. So the first one we have here is going to be kind of difficult for us to parse out here because that's a whole bunch of zeros. Now the easiest thing to do it is groups of 3, right? So I have a group of 3, 3 zeros, then I have 3 zeros, 3 zeros, 3 zeros, 3 zeros, and so on, and so on, and so on, and so on. Groups of 3 are easy to do in terms of zeros because you're used to doing them like thousand, million, billion, those sorts of things. So whenever you do them in groups of 3, it's really easy to do. So if you look at it in groups of 3, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 groups of 3. So if I have 9 groups of 3, that's 27. So I know that I'm going to have a times 10 to the 27th. Okay, and I know I'm going to have 1.67. And now the last thing I need to do is decide whether this 27 is going to be a positive or a negative. Now remember how you do this is you say, is this a large number or a small number? Is it a number less than 1 or is it a number greater than 1? And because it's a number less than 1, because we have point and then 000 stuff, it's a really small number, so I know it's going to be minus 27th. Now I want to make sure that I put my units there, so I would put the kilogram there. In the second one, remember this is a number that is larger than 0, so since it's larger than 0, I'm going to end up with a positive exponent, and if you do this correctly, you're going to get something like 3.1557 times 10 to the 7th seconds. Okay, and then this final one, you should end up with something like this. Like I said, once again, please make sure that you can go from here to here and you understand the reason why in each case. Next, it says convert the following metric measurements to the correct metric prefix using dimensional analysis. Okay, so whenever you do this, the first thing you need to do is say, okay, what is dimensional analysis? And dimensional analysis is the method for keeping track of your units. So what I have is 12.3 milligrams, and I want to convert it to kilograms. Now you could do it in one step if you kind of memorize all these different conversions, or you can do it step by step. So the first thing that I'm going to do is I'm going to go from milligrams to grams, because grams is the base unit. So let me give us a little room right there. and I want to say that there are 1,000 milligrams in 1 gram. Now, if you're not sure about that, you can refer to your metric prefix chart, but there are 1,000 milligrams in 1 gram. So now you come to the next thing, you say, all right, so I want to go from grams to kilograms, and it's the same conversion. So you have 1,000 grams is 1 kilogram. Now, whenever you're solving this, you multiply by the top numbers. So I'd say 12.3 times 1 gives me 12.3 on the top. On the bottom, there's nothing here. Now, since there's nothing here, that doesn't mean 0, because 12.3 over 0 is not 12.3. It's 12.3 over 1. So it would be 1 times 1,000 times 1,000, which is 1 times 10 to the 6th, or a million, however you want to write it out. So in order to figure this out, I have to take 12.3 and divide it by a million, and I can do that in my calculator. And when you do that, you should get 1.23 times 10 to the minus 5th, and if you look, kilograms. And it should make sense that I have a very, very, very small number of kilograms if it's 12.3 milligrams. So it should be a really, really small number for kilograms. Okay, and the next one, you can actually do this in one step if you know that nanometers to meters, that there are 1 times 10 to the 9th nanometers in 1 meter. Now, if you set up your dimensional analysis correctly, this can be done in one step. And when you do this, you should get something like 6.723 times 10 to the minus 8th meters. And the last one, you have 34.65 milliliters, and you're trying to go to centiliters. So now one of the interesting things you can see is you can say, okay, well, there's 1,000 milliliters in 1 liter, and there's 100 centiliters in 1 liter. So if you kind of take this out as the middleman, you have that there's 100 milliliters is equal to 100 centiliters. Well, if you divide both sides by 100, which you can do because you're dividing both sides out, you end up with 10 milliliters equals 1 centiliter. So you can go ahead and use that metric conversion, and if you do it, you get 3.465 centiliters. Okay, now we need to talk about the fundamental units of measure. The fundamental units of measure are really the only things that you can measure. Now you have length, which is generally measured in meters, and volume, which we talk about a lot. Volume is a derivative of length. It's length times length times length. Mass we talk about quite a bit. The standard unit of mass is actually the kilograms. Now it's very likely that you would use kilograms in physics, but in chemistry, kilograms tends to be a very large unit. So even though the kilogram is the standard unit for all mass, you tend to see grams in chemistry and you tend to see kilograms in physics. Time has a standard unit of a second, and temperature has a standard unit of Kelvin. Next it says convert the following into standard units. Now the first one that we have is a temperature conversion, and you see it as 105 Fahrenheit. 105 Fahrenheit is a really hot day in the summer. So the first thing that you need to realize is that you want to get it into Kelvin. Now you don't have a direct conversion from Fahrenheit to Kelvin. Instead, what we have is one from Fahrenheit to Celsius. So the first thing we would do is we would convert Fahrenheit to Celsius. And that formula is Celsius is equal to 5/9 of F minus 32. Okay, and that's our formula. So what I would do is I would take 105 and I would plug it in here. And in my calculator, I would do 105 minus 32. Then I would multiply it by 5 and I would divide it by 9. And that would give me my units of Celsius. Now your units of Celsius are going to be smaller than 105. Okay, it should be around 40 or something like that. So now once you do this, whatever you get for your Celsius number, you have to convert to Kelvin. And the temperature conversion that we have there is Celsius plus 273 is equal to Kelvin. So you would say Kelvin ends up being 313.7 Kelvin. Now if you notice, it's actually not called degrees Kelvin. It's just Kelvin. There's no degree symbol because Kelvin is an absolute scale. The next thing you would need to do is you would need to convert this. 250 centimeters is a length, so you need to convert it to the standard unit, which would be of mass, which would be, oh, excuse me, of length, which would be the meter. And so when you do that, you should end up getting 2.5 meters. And finally, you should be able to convert this last one, so you get 0.35 seconds. The next section that we have is on algebraic rearrangement. It's really important that you be able to rearrange equations to look for the variable that you're trying to solve for. So the first thing that we want to do is we want to make sure that that we can get the equation to look like we want to. Now we have an equation W equals FD. Now it doesn't matter what these variables stand for because it doesn't matter for these particular examples. You're just trying to rearrange the equation. So if you look at this, you have W equals FD, and then they're multiplied by one another, and you want to get f to be by itself, so you have to get rid of the d. So if these two things are multiplied by each other, you have to do the opposite function. So in other words, I have to divide both sides by d. When I divide both sides by d, that allows me to get rid of the d here. But now I've changed this equation. It's no longer the same equation because I did something to one side without doing it to the other. So in order to make my equation consistent, whatever I do to the right side, like divide by d, I have to do to the left side, which is divide by d. So the answer that I would have would be F equals W divided by d. Okay, this next one is a little bit trickier because you're trying to solve for acceleration, and you have things that are multiplied by acceleration and things that are subtracted by acceleration. So every step that you take has to be going towards isolating the a variable. So the first thing that you want to do is you have two terms. So you want to get rid of the term that doesn't have a first. Now it's plus vi, so the opposite would be minus. Then once you've isolated the term 2ad, it's very similar to what you had before. You just have to find a way to isolate this. If you do this correctly, you should get something along the lines of a equals vf squared minus vi squared divided by 2d. And the last one, if you do it correctly, should end up being something like this. V equals 2ke divided by m with a square root symbol. Next, we go into graphing. Whenever you do a graph, it's really important to be able to look at a graph and determine whether or not it makes sense to do the graph. So the first thing that we have here is we have a distance versus time pie chart. Now, one of the things that's clearly wrong with this graph, it does have a title, yes, but these things aren't labeled. Are those distances? Are they times? Are they both distances and times? You have no idea of saying. So the first thing is there's no key. The second thing, this is clearly a wrong choice here. The only time you would ever do a pie chart is when you're comparing a part to a whole. Is there such a thing as a whole distance or a whole time? Well, I mean, in theory there could be, but you can't really compare two variables in a pie chart. It just doesn't work. So you're comparing the part. So if I were to say the part of the distance that I walked, jogged, ran, and sprinted, okay, you could do something along those lines, but it doesn't work for distance versus time. Okay, in this graph, it's really important. If you see you've got a very clear looking graph right here, but you're missing something right here and right here. And finally, you do have labels on this one, so that's good. You do have labels right here, and yes, you can have labels on this side of the axis. But one of the interesting things about this is it's not following the same consistent pattern that we do with our data. Remember, we're looking for patterns in the data, and we want to be able to draw a smooth, continuous line, not jagged, 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 jagged. So now what we need to do is we need to be able to graph our data. Okay, whenever you graph your data here, there's several steps that you need to do. The first thing you need to do is you need to look at your variables and you need to decide on what is the independent variable and what is the dependent variable. Generally, they put them in order for you. So this is my x variable and this is my y variable. And that's true because how far you go does depend on how long you walk, but time does not depend on where you're standing or how far you've walked. So because of that, we can say that time is going to be on the x-axis, and the standard unit is the seconds. Now it really should say seconds here, but we're going to assume it's the standard unit since it doesn't say anything else. Now if that's time, this right here has got to be distance, and that's going to be the standard unit of the meter. So now I would title my graph, and whenever you title your graph, you always do y versus x, or distance versus time. And when you do that, now you've got your title to your graph. The very next thing you do before you plot your points is you have to develop a scale. And a scale is a way of fitting all the points on the graph to make sure, number one, that they all fit, and number two, that you're not squeezing the graph into a little quadrant right here. You want to make sure that you use all the space that's available to you. So the first thing that I'm going to do is I'm going to look and I'm going to say, okay, count these boxes. There are 20. Count these boxes. There are 20. So because of that, I know that I have 20 available boxes on the x-axis and 20 available boxes on the y-axis. So I'm going to look at my x-axis first. I need to figure out how to pick points from 5 to 0. When I pick points from 5 to 0, I have 20 available boxes. So when I do that, I get 5 minus 0 over 20, which is 0.25. Okay? So when I get 0.25 as my option, that means each one of these little boxes could be 0.25. And that's something that you could clearly do, and it would make it fit really well on the graph. And that's okay. You can actually use 0.25. I generally use 1s, 2s, 5s, and 10s. So I would personally round this to 0.5, but I wouldn't take off if you decided to leave it as 0.25. So whenever you make something, I'm going to go ahead and make it 0.5. So my x scale is 0.5 seconds. So that means each one of these lines right here is 0.5 seconds. Now I don't have to label all of them. What I can do is I could label every two. And you could just say, wow, that's 0, 1, 2, and then 3, 4, 5. And so I've labeled my scale right here and I know what it is. So now the next thing that you would do is you would say, all right, now that I've done that, I can scale my distance term. So I have to go from 25 to 0, and I have 20 available spaces. Now when you do that, you actually get 1.25. And 1.25 is kind of a messier number because instead of going 0.25, 0.5, 0.75, 1, 1.25, 0.5, points, you get 1.25, 2.5, 3.75. It doesn't work as well as far as keeping track of where you are on the graph. So I would round this one, and you have to round up. You always have to round up, so this would be 2. If you round down to 1, not all your data will fit on the graph. So once I've rounded to 2, I'm going to say that my y scale is 2 meters, and then I can plot out these points right here. I could say each one of these is 2, so I could say 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, and so on and so on and so on, until you get to the top here, which would have a value of 40. Once you do this, you can now plot your points. Your first point is very easy to plot. It's at 0, 0. Now remember your scale when you're plotting your points. Okay, the next point is 1, 5. Okay, 1, 5. Well, 1 is not the first line, it's the second line on the x-axis. And it's not the fifth line up, but it's the 2.5 line up. So this right here would be your second point. Okay, and if you were to continue to do this, you go to 3, and then that would be at 10, or excuse me, 2, and that would be at 10, and you would go to 3, and that would be at 15, and you would develop a nice straight line in this case. And since you have a nice straight line, you would draw it and you would connect those points. Okay, the next graph is a little different in terms of scaling. If you look, the first data point starts at 10 and it goes to 200. Now, when I would develop my scale, instead of going from 20 to 10, I would probably just go ahead and do 200 to 10. I would do 200 to 0 because it makes sense to put 0 on the graph when you go all the way to 10 from 200. You might as well go to 0 and make the graph look, see what it does as it approaches 0. Same thing here. Instead of 19 and 1, Why don't we just do 20 and 0? It makes it a lot easier, and you get really good numbers as far as your scale is concerned. You get 10 and you get 1. So I can actually make my acceleration scale 1 meter per second squared, and I can actually get my x scale to be 10 kilograms. And whenever you generate this graph, the first thing you'll notice is that it has a curve downward. Now if you notice it's got a curve, and I didn't draw it like, you can't draw it like this. You're not allowed to do that. Instead, what you do is you have to draw it as one smooth, continuous function, something along those lines. Make sure you label your axes, make sure you title your graph. Finally, you come to the last graph, which is once again going to be a straight line, something along these lines right here. It would be appropriate for you on this graph to have a scale of 10 and 2. I'll let you figure out which one is which. You should be able to title the graph and label your axes based on what you see. Just know that this is the independent variable and this is the dependent variable. Okay, this concludes the Unit 1 remediation guided practice. If you are still having trouble at this point, you need to make sure that you see your teacher before you work on the independent practice.